My apologies for the background noise in this video, but my children just got some new Legos. They might be putting them together. Anyway, so next I look at so we're continuing with applications of the geometric series and the term-by-term calculus theorem to find power series representations of functions. So this one, natural log of 1 plus x squared, well, that's not geometric to start with, but if we differentiate it, we get 2x over 1 plus x squared, which is something we can use the geometric series result to expand. So this expands to that. So we have minus 1 times 2 to the times x to the 2n plus 1. And then to get back to f of x, we can integrate the derivative. And so we do that. All right. And term by term calculus, I mean, I guess to be fussy, I probably should have plus c here, right? And that same c is down here. But on the other hand, when we plug in 0, we get natural log of 1, which is 0, so the c ends up being 0, which is not exciting, but there it is. Beware, sometimes the constant that you recover in such a problem can be non-zero, so we got to think about it. And there you have it. What? Hey. Well, that's just not right. So it's not. This is not. Oh man, I'm sorry, guys. What's going on here? This that we just found is not it's not this function, right? No. This is equal to the natural log of 1 plus x squared. That was the whole point. I found the power series to represent the derivative, right? Then I integrated term by term, which brings me back to f of x, which is the natural log of 1 plus x squared. All right? Well, sorry, I do make mistakes. All right, anyway, next up here, I have some select solutions from the 6th edition of Stewart's Calculus. So here's so we have been, in the last couple of examples, using power series, geometric series to find expansions of not the function directly, but its integral or derivative. So this first example is more basic. It's just if you have that function, we can understand it as a power series by using the geometric series result. So now, technically speaking, this function has a domain that is far beyond minus 1 to 1, so only local to 0 do we represent the function by this power series. All right. So, I mean, technically speaking, it's not the power series expansion for the function everywhere, but just close to 0, we have this result. So, again, a equals 3, r is equal to x to the 4th, and so we get that. And the geometric series result says that the interval of convergence here happens to be minus 1 to 1, which means the radius is 1, and of course the center is 0. Next up, look at the power series, find the power series for f of x equals to 1 plus x over 1 minus x. Now this one we just break up into 2 pieces, and we use the geometric series result on each piece separately, which gives us x to the n and x times x to the n plus 1. And then when you have something like this, you want to clean it up, all right? So we can combine these series by making a substitution. We'll let k equals to n plus 1 on the second one, and then we get k equals 1 to infinity, like so. And over here, I split off n equals 0 to get that 1, and I started n equals 1 to infinity. So I took this and rewrote it as that was that. The reason I did that was so that then I can see that this and that are in fact the same thing. So I can combine them and get 1 plus twice the integral from 1 to infinity of x to the n. There's the power series representation of 1 plus x over 1 minus x. And again, the interval of convergence is minus 1 to 1 because of the origin of this calculation being from the geometric series. Example 10, problem 10 from the 6th edition of Stewart's Calculus. Find the power series expansion for x squared over a cubed minus x cubed, u. So here, again, I'm going to use the geometric series, and to do that, I have to factor out a cubed to create this 1 downstairs, and that creates a radius of x cubed over a cubed, And so the first term is x squared over a cubed. All right, so again, I identify this radius in that first term, and I'm off to the races. A r to the n equals 0 to infinity, geometric series result. And what happens? Do algebra, we get 3x to the 3n plus 2 over a to the 3n plus 3. And there you have it. And the interval of convergence is when the radius has absolute value less than 1. So that's x cubed less than a cubed, which of course amounts to the absolute value of, oh man, I have, I mean this implies that the absolute value of x is less than that, than a, right, which gives us that interval of convergence right there, okay? Make sure you can actually see what I wrote. Okay, you can. Good, good, good. Moving along here. This time we're asked to use partial fractions to help find a power series expansion for 3 over x squared minus x minus 2. So partial fractions here is a over x minus 2 times b over x plus 1, because when we factor the denominator, we get x minus 2 times x plus 1. So use the usual song and dance partial fractions. We get 1 over minus 1 over x plus 1 plus 1 over x minus 2. Then we have to, what? Sorry, I'm confused all of a sudden. What happened here? I think a is 1. 1 over x minus 2, great. B is minus 1, okay. What happened here? What happened to my... I understand this. This is 2. I factored out a minus 2, rather. And that gives me 1 minus x over 2. That's this term. But this right here, I think I got a typo. That's supposed to be a 1. Let's hope that that's as far as this typo goes. 1. Right. All right, continuing. Let's see here. So this one, yeah. See, I have undone my typo in the next step. Minus 1, n equals 0 to infinity of minus x. This is 1 minus a minus x gives me a radius of a minus x and an a of minus 1, hence the minus. And then over here we have a is equal to minus 1/2 and the radius is x over 2. Both of these by the geometric series result. Now this goes to that, assuming that the absolute value of x is less than 1. This goes to that, assuming that the absolute value of x over 2 is less than 1. And I don't know. Come on. This is not right. This is not right. So you have, here's the deal. So we've got absolute value of x less than 1. And what else do we need? The absolute value of x over 2 is less than 1. Now that does not say 1/2. That says that the absolute value of x is less than 2. In other words, this is no restriction on that. So this right here is the weakest link. And so actually the IOC here is minus 1 to 1, if we're careful. All right, so hopefully I can find these silly mistakes as we go. All right. Of course, I probably could have checked my answer in the back of the book and seen that I should have gotten that. Because this was an odd problem, and probably if I'd checked, I would have seen that I was wrong here. But anyway. And then again, I combine these two into a single thing because they're both x to the n and they both start from 0. So to add the series, I can just add the coefficients, namely minus 1 to the n plus 1. And minus 1/2 to the n plus 1. Well, and the minus is out front. There's not it's not alternating. It's just minus and then 1 over 2 to the n plus 1. All right, moving along here. Number 17 of my many examples that I have here. So at number 17, we're asked to find the power series expansion for x cubed over x minus 2 squared. All right, so this one, what I do is I integrate. I'm going to just focus on ignore the x cubed and just focus on the 1 over x minus 2 squared, because I know if I integrate that, it gets me something that's a reciprocal, which is thus geometric, right? I can do a geometric series on the integral of g of x, and I get that. So the g of x is actually n over 2 to the n plus 1 times x to the n minus 1, you know, and great. So then I take that g of x, I multiply by x cubed, and there you have it. You notice what happens, the n over 2 n plus 1 stays the same, and then that becomes x to the n minus 1 plus 3, which is n plus 2. And there you have it. So sometimes we can use a little bit of algebra combined with the other technique. Like this time I don't want to mess with x cubed and this at the same time, so I just split off the x cubed, focus on the 1 over x minus 2 squared, integrate, geometric series, differentiate to get back, and then multiply by x cubed. And this time the radius of now I figured out the radius of convergence is 2 if my radius is x over 2. This is a glaring contradiction to that. I just didn't see it when I wrote this. I'm so sorry, guys. All right, moving on. All right, number 18. Find a power series for inverse tangent of x over 3 and state the radius of convergence for the series. So we differentiate inverse tangent, and that gives us 1/3 over 1 plus x squared divided by 9 by the chain rule. Of course, we all know how to differentiate inverse tangent. That's Calc 1. We know that. And so I've got geometric series. A is 1/3, r is minus x squared over 9. And I do the algebra. That gives me so 9 is 3 squared. So this gives me a 3 to the 2n from that. And then that 3 gives me a 3 to 2n plus 1. Take my minus and factor it out to minus 1 to the n, and that leaves me an x to the 2n. Right? That's the derivative. It's a series representation for the derivative of the function we're interested in. So we integrate to get back to f. This is constant plus the term-by-term integral of that, which is minus 1 to the n over 3 to the n plus 1 times 2 to the n plus 1, right? 2 to the n plus 1, 2 to the n plus 1, integrating term by term. Again, the constant works out to 0. Eventually I'll find an example without the constant being 0 at some point. Eventually it's going to happen someday. Anyway, here it is. Inverse tangent of x over 3 is that series right there. Of course, you could have substituted u equals to x over 3 into our earlier example for inverse tangent and get the same result. All right. So in this case, the radius of convergence comes to us from the fact that the radius was x squared over 9. And if that's less than 1, that's going to be true if the absolute value of x is less than 3, like I say down here. All right, well, yet more examples coming up. Here we go. Calculate a power series solution to the integral of t over 1 minus t to the 8th. Well, this is almost directly geometric. We use the geometric series to convert the integrand to a power series in t. Well, that's not a power series in t just yet. We have to clean it up. We get t to the 8n plus 1. Now it's power series in t. Then by the term-by-term calculus theorem, we integrate term by term. We get 8 to the 2n, t to the 8n plus 2 divided by 8n plus 2 plus a constant. There you go. That is a power series form of the integral of this. Now notice here we need the radius to be less than 1. That gives us that the absolute value of t to the 8th is less than 1, which is to say that the absolute value of t is less than 1. So here the radius of convergence is 1. Remember that integrating and differentiating will not change the radius of convergence, and I'm always using this fact over and over and over in the problems I've been talking through in this video. All right, it should go without saying, as I say sometimes, although it seems like I'm saying, so I don't know, I guess it goes with saying, that, you know, you're going to need to pause and work through these things, right? Nobody in their right mind could follow me without pausing. Here's another one. Integrate inverse tangent of x squared dx as a power series. Find the radius of convergence. So following number 18, which was, what did I do? Number 18, what was number 18? Number 18. It seems like forever ago that we did number 18. Where is number 18? Number 18. Ah, number 18. there we found the power series for inverse tangent of x over 3. All right. So I guess what I actually, you could just piggyback this on top of that result, but I think what I decided to do was to actually follow the same method as an 18. I'm not actually using 18. So this differentiate gives me that, excuse me, then geometric series. Clean it up. By the way, I see the radius of convergence was 1 from that step. That radius of convergence will stick with us for the rest of the calculation. Then I integrate to get back to the function, term by term, right? Evaluated at 0, inverse tangent of 0 is 0, so my constant 0 once more. And now that I have this as a power series representation of the integrand, I can do the integration. So the integral of inverse tangent of x squared is the integral of that series, which term by term integrates to that. There you have it. That is a power series representation of the integral of inverse tangent of x squared. And that brings us to our next example. All right, it's very exciting. So many examples. So finally, the other thing we can do, and I haven't done this is a genuinely new example, is if we can find a power series representation of the integral of the antiderivative, right? Then we use FTC2 to take the difference, and when you do that, we might end up with an alternating series, which then we could estimate. So let's see how that goes here. So again, I'm going to find a power series representation of the integrand using my geometric series tricks at the moment. The FDX is that, which geometric series to that, which gives me that. And then I think I lost there's something that was lost here in the process of scanning or something. That's supposed to be 4n plus 3. All right, there we go. Put it back. You can see that in the next step, because when we integrate term by term, we get 4 times minus 1 to the n divided by 4n plus 4, x to the 4n plus 4. So this should match that when we do the term by term integration. So hey, there's your integrand, and now, okay, finally I have to figure out that the constant 0 again, right? And now I'm going to actually go ahead and, instead of writing the full series for the integrand, I'm going to write it out term by term. So the first few terms in this are x to the 4th minus 1/2 x to the 8th plus 1/3 x to the 12th minus 1/4 x to the 16th plus dot 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 dot. Integrating from 0 to 0.4, so I do fundamental theorem of calculus part 2, take the difference of my antiderivative at the upper versus lower bound. The lower bound gives me 0, the upper bound gives me, oh yeah, an alternating series. So we know we can estimate that by as far as we go, and then the next term is a bound on the error. So I say this is 0.002034 doing what? I just kept the first 1, 2, 3 of these, I think. And then the next one I haven't written is actually 156 times 0.4 to the 17th power, which, by the way, is about 0.000001. So, yeah, that's good to 6 decimal places. There's more. There's more. So sorry, guys. I don't know what's over here. There's more that was lost in the... Why is there a fruit fly in front of me? Sorry. It's probably because we have fruit. Those mangoes are delicious, but they do come with consequences. Anyway, there are 1, 2, 3... Oh, that is 6. I'm not sure what's over here. I don't really care. So those 6 digits are certain because the error is in the 7th place, at least. All right. So actually, what did I say here? All right. Oh, actually, I think I could have actually gotten away with just taking... I'm not sure what I'm saying here. This may have been overkill. All right, anyway, let me not belabor. I hope you get the spirit of the idea here. It's just that we can find a series representation for the antiderivative, and then FTC2 might produce an alternating series which we know how to estimate already from previous work. Now this one's a little bit different. Here we're asked to show that this series, minus 1 to the n times x to the 2n over 2n factorial, is a solution to y prime prime plus y equals to 0. So this is opening a larger can of worms, which is, what do we mean by a solution to a differential equation? And the answer is pretty simple. It means that when you take that and you plug it in and you do what the differential equation says, it works. So let's try. So we take it, we differentiate, get that, and you notice when n equals 0 we drop it out. We differentiate again, we get, notice I took the 2n divided by 2n factorial and I simplified it to 1 over 2n minus 1 factorial. Differentiate again, I get 2n minus 1 times x to the 2n minus 2, and this will simplify again, alright? We can drop the 2n minus 1 factorial in favor of 2n minus 2 factorial. And then finally, let's see here what's next. So I'm like, alright, I'm going to make a substitution of 2k equals to 2n minus 2. And when I do that, if I have n equals, n equals to 1 is the lowest thing here. Put in n equals 1, that gives us 2 minus 2, which is 0, so k equals 0 with the substitution of 2k is 2n minus 2, which is otherwise known as n is equal to k plus 1. Alright? So 2n minus 2 is 2k, so this is a 2k factorial, right? 2k factorial, 2k, and my n is k plus 1 minus 1 to the k plus 1, which you can factor a minus out. Then you've got k equals 0 to infinity, minus 1 to the k over 2k factorial, parentheses 2k factorial, x to the 2k. In other words, this is exactly what we started with, but with a minus, which means that we've got f prime prime of x is equal to minus f of x. Therefore, f prime prime plus f equals to 0. Consequently, whatever function this is, it is a solution to this differential equation. All right? I'll give you a spoiler. That function is cosine. We will soon learn how to derive that. In fact, at the moment, we are in a transitional stage. We are only using geometric series and term-by-term calculus to find power series expansions of functions. We'll soon learn something called Taylor's theorem, which will give us another way to find power series representations of functions. However, I would point out that the techniques that I've shown you in this video will almost always be the superior technique for this class of examples. Taylor's theorem, in some sense, is a weapon of last resort. It's good for generating a few terms, but if you want to generate the whole series expansion, it's hard to beat what I've showed you in this video. I wish more students would learn this lesson because it's important for future courses as well, especially complex analysis, which you might take at some point. Anyway, thanks. That's it for this video.